So welcome to the Friday Transportation Seminar. My name is Chris Monsere. I'm an assistant professor in the Civil Environmental Engineering, and I'll be delivering the seminar presentation today. So together with my colleagues Rob Bertini, Miguel Filiozzi, Jennifer Dill, and John Glebe, we co-organized this Friday Transportation Seminar. So with that, we'll get right into the presentation. And the title of my presentation today is Using Archived ITS Data to Measure the Operational Benefits of System-Wide Adaptive Ramp Metering System. And before I begin, I'd like to recognize the PI on this project, Rob Bertini, and two students that helped us on the project, Oren Eshel and Chengyu Dai, who's in the room here. So the outline of the presentation today, I'm going to talk a little background, just briefly, what is ramp metering, one slide about the swarm algorithm, the methodology we used in this analysis, some results, and conclusions. So ramp meters, and for those on the web, the images, there we go. So ramp meterings at their basic level are traffic signals at the end of freeway on-ramps. So they have two main goals. One, to limit the amount of traffic entering the freeway, especially as the freeway nears capacity. So to keep the freeway operating below capacity. And two, to break up platoons of vehicles as they're entering the freeway. So generally, if they've been discharged from an upstream traffic signal, the ramp meter intends to break up the platoons of vehicles to space out the vehicles entering the freeway. So this is an old technology, an old operational strategy for improving the operations of performance on freeways. And I don't list any of the studies, but many of the studies have shown the potential for ramp metering to improve traffic flow, traffic safety, and air quality by reducing congestion and fuel consumption. And it also has a side benefit of managing demand by discouraging short trips. So if the appropriate ramps are metered, it will discourage short trips on the freeway, and people may take the arterial instead. So the freeway should be used at its capacity for longer section trips. So, I mean, there's a lot of work in sort of optimal ramp metering strategies. They either come in two kinds, fixed, where the metering rate, the amount of vehicles that are let on per time, are already pre-decided by some historical pattern, and so the timing is fixed, and it's independent of the traffic conditions on the freeway. More modern systems are adaptive, meaning that the metering timing, when the meters come on and what rate they allow vehicles to enter the freeway, can change depending on the freeway conditions. So if the freeway for that particular day, say it's a weekday with light traffic, the meters may not come on until later, and then if they do come on, they may meter at a higher rate, allowing more vehicles onto the freeway. So any ramp metering strategy really is a trade-off then between imposing delay on vehicles trying to enter the freeway and those vehicles on the freeway. So if you make the metering restrictive, you're going to build large queues at the on-ramps and impose delays on those vehicles while maybe keeping the main line with less delay. If you allow more vehicles onto the freeway, eventually it's going to cause congestion on the freeway and impose more delay on the main line. So it's always a trade-off there, and you're also always limited usually by how much ramp storage you have. So a particular ramp may only be able to hold so many cars in queue before it backs up into the arterial system and causes other problems. So it's kind of a balancing act between those three parameters. So the ramp metering started in Oregon in about the 1980s. It has been fixed time or a pre-time system until relatively recently, which was the focus of this project. And they elected to implement an algorithm called SWARM, the System-Wide Adaptive Ramp Metering. That's an algorithm implemented by Caltrans in Southern California. So they've not been, the Caltrans evaluations, they've done a few, but they've been in-house, and they've not been that extensive in terms of their evaluation. But they found benefits for mainline travel, but they also found that the swarm algorithm was fairly restrictive, and the queues at the busiest on-ramps increased by 40%. And the swarm algorithm competes between a local, so at the ramp, optimal metering, and a metering looking at over the corridor in a more global sense. So it's evaluating which metering is appropriate based on local conditions, but also on the freeway conditions, and then it selects the appropriate metering rate. So in our study, we conducted a pilot study on Oregon 217 southbound, which helped us set up the parameters for the remaining study. I'm going to talk today about the 3 other corridors that we evaluated in the full-scale study. So we looked at I-205 northbound in September, October 2007, and we looked both in the morning peak and the PM peak. And we looked from the Gladstone on-ramp, which is down here, to the Division exit. So that was the extent of our evaluation on 205. And then on 217, we looked along the whole corridor, but we only looked in the afternoon. So our approach was they ran the meters for 2 weeks in the fixed time or the pre-time mode. We were collecting data all the time through our portal, which is our regional transportation data archive. So everything that was happening on the mainline freeways by the detectors was being archived there. Then they switched over and ran the meters for 2 weeks in the swarm mode. So we went through the data pretty thoroughly, looking for data quality, weather, and incidents, and I'll show which days ended up being excluded from our analysis on the next slide. The last bullet was our attempt. When we had done the pilot study, we had analyzed the ramp queues with video. And so there was a number of students that spent a lot of time watching video for the ramps. And we did it, but it was time-consuming and labor-intensive. So our approach to look at the ramp queues on this project was to use these little sort of hardened field computers called programmable logic controllers to do a simple queuing analysis, because there are loop detectors at the bottom of the ramp and detectors at the top of the ramp. So using sort of simple queuing, we could measure vehicles coming in and the time they came in, and then measure the time that they came out, and we could keep track of the queues on the ramp. Unfortunately, we had some data collection or data quality issues where this, while this approach should have worked, the data we got out looked fairly, on some days it was good, on some days it was not so good. So we ended up not being able to use the ramp queue data here. So, but what we did get from these programmable logic controllers is we did get on and off times from the ramp meters, which is not logged in the system anywhere. So that was a valuable piece that we got in our analysis. So the methodology we looked at for the performance measures, we looked at sort of the traditional performance measures, VMT, vehicle miles traveled, vehicle hours traveled, and then the primary focus measure that we were looking at was delay. So we also, although we didn't have a large sample, so we had 10 days before and 10 days after, we wanted to break the days down and look at how the swarm ramp metering algorithm performed on similar congested days. So it was a subjective, we had a set of criteria that we were using to try and determine how we would classify the corridor, both in time and in space, on how we would classify it congested. And we ended up coming up with these 4 categories of either least, moderately, highly, or very highly congested. And then we looked at the performance of the ramp metering on those 4 overall in the corridor and on those 4 classifications of the congestion. So I mentioned we looked at the data for both weather, that's the thunderstorm icon, incidents, which was the next cleaning filter we used, and the last one was data quality. So I'll talk quite a bit about the data quality impact of the swarm algorithm on the data collection system. But there were, this is in the pre-time situation, there were 4 days that were excluded for data quality issues. So we didn't get enough data in those days. We excluded them from the analysis. And there were 2 days where the weather was sufficient that inspecting the data, we sort of determined that the weather had an impact on the congestion for that day. So we excluded those days. In the swarm periods, the 2-week swarm periods, there were 2 incidents on 205 northbound in the PM, 2 weather days, and you can see that there was quite a bit more days lost due to data quality, and I'll explain why a little bit later in the presentation. So this is just a snapshot basically of the heart of the analysis data that we used. So again, this is from the Portal Data Archive, and this graphic shows, so on the x-axis is time from about 5 in the morning to about 8 o'clock at night. The y-axis is distance, so travel is from the bottom of the graph to the top. And the color indications are the speed readings, the average speed readings from each of these detectors across all lanes. So the red speeds are low speeds, green is higher speeds. And this kind of summarizes the data that we used in the analysis. You can see here that this is probably not congestion. This is definitely data quality issues. So when the detectors are reporting low speeds over these large blocks, those were data quality issues. These other points on the graphic, the purple dots are the fixed time start times of the ramp meters. So at 3 ramps, we were able to deploy those programmable logic controllers. So at Sunnyside, Johnson Creek, and Powell, we were able to have those devices out there. The purple dots are when the ramp meter came on during the fixed time, and the blue line is when the ramp meter came on during the adaptive time. So like on this, so at Sunnyside, in the pre-timed, it came on right at about 6:30. But on this particular day, the adaptive, the ramp meter didn't come on until much later, about 7 o'clock. And it stayed on longer than it would have in the fixed time. And conversely here, it came on earlier than it would have on the fixed time. So the purple dots are the pre-timed or fixed time, and the blue lines are the adaptive. So that's kind of just a quick summary, a good picture of the data we used in the analysis. So I'm going to present 3 of these tables, and I'm going to walk through it. It's kind of busy, but I'll walk through the table, and then hopefully it'll be a little bit more clear. So on the first column is the levels of congestion. So we had least, moderately, all the way down to very highly congested. And then the last row is for the whole corridor. So this is for I-205 in the afternoon peak period. The second column is the number of days we were able to compare pre-time to swarm. So the first row, the least congested, we had 1 least congested day in the pre-time, but no in the swarm period. So that's why all the rest of the row is dashed. The 3 performance measures we looked at, as I mentioned, VMT, VHT, and delay. And then the table shows the % change from the pre-time period to the swarm period. The delay column and the standard deviation of the delay I've sort of color-coded as green being a good and red being bad and gray being no comparison. So we looked at the delay and its change from the pre-time to the swarm period. So overall in the corridor in the I-205 in the afternoon peak, there was an 8% decrease in delay from the pre-time to the swarm. There were 8 days pre-time to 6 days swarm. And there was a decrease in the standard deviation of the delay, which is what we want. Another measure we were looking at as sort of an indication of reliability. So you may have delay, but how variable was that delay? In almost all cases except for 217 northbound, which I'll show you at the end, the standard deviation of the delay decreased.
Question about delay?
Yeah.
Is that just on the corridor and not including cars on the ramps?
Yes. Yeah. Good. Yeah. Thanks for clarifying, Dave. So we did not know anything about the ramp delay. So, but I'll let you. Well, I'll say a little bit about that based on what we've observed in the empirical data. We can say something about the ramp delay. So, so this is just the mainline delay. So even though the overall corridor had an 8% sort of improvement in delay, the moderately congested time periods is where you would expect ramp metering to have sort of the most positive effect. We actually observed a 30% increase in delay. We did a t-test of means, but because the delay was so variable and the sample so small, this p-value, almost only one of the tests in all of these days came out as significant. So But dividing the days up into congestion level was more for informative and sort of diagnostics than necessarily comparison, route comparison. In the highly congested and very highly congested, in retrospect, we probably should have combined those two. But there was, in this case, the swarm algorithm did better than the pre-time period. So I don't know why the graphic, the color is a little distorted. On my screen, everything's red, yellow, green. I guess yellow becomes orange on these projectors. But this graphic shows, and you can't, the legend is cut off. So this is the change in vehicle hours. So this is the change in delay from the pre-time to the swarm period. So the dark red areas are where in space and time the delay on the corridor was worse in the swarm period. The lighter colors, the green colors, is where the delay was improved in the swarm period. So we use this here to diagnose where in space and time there was where the improvements were. So instead of just looking at the overall corridor, there was an 8% increase and 8% decrease in delay. Where was that decrease? And so just highlighting these two areas are where this is where the swarm did worse than the pre-time. So we wanted to kind of zoom in to this area. And this, we also made these plots for each of the various congestion levels. And again, it's the same, for the moderately congested where there was a 30% increase in delay, down at the beginning of the corridor at the Clackamas lawn field detectors, you can see that's where a large chunk of the increase in delay comes. And there was also a little slice here at the Sunnyside Foster, Johnson Creek area between about 3:30 and 4. So the Clackamas area, the reason we did some, and I'll show you, we did some diagnostics like this that I'll walk through. And for that ramp metering station, the conclusions are about the same as we came from this one. So the question was, why worse? So why did the swarm ramp metering algorithm perform worse than the fixed time? So these plots, the pre-time condition are for the three stations, so Sunnyside, Johnson Creek, and Foster. And they're on the top row. So the top row is the pre-time condition. The bottom row is the same three stations for comparable congested days on the bottom row. So there are three lines and two vertical lines on each graph except for the Foster swarm station. The yellow line, this top line, is the observed mainline speed, and it's read off the secondary y-axis. So it goes from 0 to 60 miles an hour. So the yellow line is the speed, observed mainline speed. The blue line and the red line are read off the y-axis, and it goes from 0 to 5,000. It's the flow rate in vehicles per hour. And the blue line is the mainline flow, and the red line is the metered flow. So we were able, in the Portal Data Archive, from the front, the vehicles passing the downstream of the signal, there's a set of detectors. So we were able to measure the flow, the number of vehicles entering the freeway. The vertical lines on each of the plots, so these are the three stations where we had the meter on and meter off times. So the vertical lines are the time the meters came on, and then this is when the meter came off. So at Johnson Creek, Sunnyside, they came on and went off, on and off, on and off. Those are the fixed time. And then this is the same data for the adaptive time. So these plots were fairly useful when we showed these to the ODOT operational people in Region 1. When they saw these plots, they started to get an understanding of things that they might be able to change in the swarm algorithm to improve it. And I'll kind of walk you through some of the things we got from these plots. So the first thing you notice is that at the Sunnyside and Foster station, even though we didn't have, for this we didn't have actually to clarify, we didn't have the data collection at Foster, it was at Powell. But we know from the timing plans when it should have came on in the pre-time. But we didn't know in the swarm time when the ramp meter actually came on. But you can see if you look at this line where the flow rate drops, that's where the meter came on. So when the meter goes down to about 1,000 or 900 vehicles per hour, you can see where the meter came on. So, so why worse? So at the Sunnyside and the Foster, if you compare that to the pre-time, the meters actually came on later in the swarm condition than they did in the pre-timed. At Johnson Creek, it came on actually a little bit earlier than it would have under swarm. Swarm came on earlier than pre-timed. So, and Dave, this goes to the ramp information. In all cases, we observed, despite what Caltrans found, that they found increases in the ramp queues. When ODOT implemented the swarm algorithm, they sort of capped or made swarm, they didn't want it to be that restrictive. So in all cases that we observed, and in the pilot study where we had the video detection, and in all areas that we looked at, the swarm algorithm actually lets more vehicles on the freeway than the pre-time situation. So, and because we can look at the VHT, sort of the overall demand, and we did it 2 weeks before and 2 weeks after, and we sort of assume that the ramp demand probably didn't change because the mainline demand didn't change very much. We can conclude, but not conclusively say, that the ramp delay had to decrease because more vehicles were getting on the freeway than in the pre-time situation. So, but in all cases, if you look where, and I should have overlaid these two for you, but if you look at where this is at here and up here, it's slightly higher. The swarm algorithm always allowed more vehicles on the freeway than the pre-time situation. And just looking at this graph here, so this is Johnson Creek Station, you can see that in the swarm period, the drop in the mainline speed occurred earlier and for a longer duration than it did in the pre-time situation. And granted, this is just one snapshot, but these are sort of the diagnostic tools we were looking at. And it sort of happened, the peak mainline flow is about that time where you saw in the delay space-time change, right where the mainline flow peaks, where swarm is letting more vehicles on the freeway, is sort of where we saw that increase in delay in the time-space window. So looking at the performance, the highly and very highly congested days where swarm seemed to perform a little bit better than the pre-time situation, doing that same type of diagnostic here, the green areas are in those same stations, Foster, Johnson Creek, Sunnyside, where a big chunk of the improvement occurred. So let's take a look at those. This is the same plot, same three stations, pre-timed across the top, swarm on the bottom. And here in this situation, you can see that the adaptive ramp metering system came on at 1 o'clock, and ODOT had allowed, that was the earliest they would allow the ramp metering to start, was at 1 o'clock. And in this case, on these highly congested days, the ramp metering timing came on at 1 o'clock. At the pre-timed, it's not coming on until 1:30, 2 o'clock, depending on the station. And you can see here that the mainline speeds on the pre-time situation on these very highly congested days drop well before the meters even come on. So the situation has gotten, mainline condition has gotten worse before the meters have even come on. But in the pre-time situation, the meters jump, or in the swarm situation, the meters were able to start at 1 o'clock. And even though they were allowing more vehicles on, they were able to sort of manage the delay a little bit better because they started earlier. The other thing to look at is, and again, this is just one snapshot from one station from one day, but if you look at the speed information across the top, and you see how much more variable that is, the oscillations in the speed, whereas the swarm, it's a little bit more dampened and a little bit more smooth. That goes to the standard deviation of delay, where we saw an improvement in sort of the variability of the speed or delay or travel time, whichever one you want to look at. So looking at the morning, swarm on 205 did across the board better in all congested conditions, and overall had an improvement about 20% in delay and in an improvement in the standard deviation and delay. And again, just looking at the map where this chunk is here, I'm not going to go through another one of those plots, but what we found by looking at the diagnostics there was that in the pre-time situations, the meters went off, but there was still quite a bit of ramp demand particularly at the Foster ramp. So you could see in the plots where the meters went off in the pre-time situation and this big surge of vehicles came on, and you saw a pretty significant jump in delay in the pre-time situation. But Swarm was able to keep the meters on until about 9:30 or 10 until that demand went away. And so at that particular station, the meters staying on longer actually improved the performance in the corridor. Now in 217, things didn't perform so well. And this was also the result in our pilot study. This particular corridor with the Swarm implementation, things were much worse with the Swarm algorithm than they were in the pre-time situation. And if you look at the spatial, again, everything is pretty, the whole corridor. The other graphs you saw, greens and reds, a little bit of mixed performance. Here on 217, the Swarm algorithm is implemented. The performance was much worse. So we sort of hypothesize or suspect that it's because there's if you know the two freeway corridors, 217 is it's a narrower corridor, a narrower freeway, sort of lower, a little bit lower. It's not design standard, but a little lower performance level than 205. But actually, 217 has higher per lane mainline flows than 205s. There's actually there's less room for error on 217 than there is on 205. And with Swarm allowing more vehicles in all cases, and here particularly, that surge onto 217 where there's not as much room to give sort of produces this picture. So that's what we hypothesize. So, and I didn't go over the data quality changes in all of those graphics because I think, as Dr. Bertini would like to say, a picture is worth more than some of the tables. And here's the percentage of communication failures on the left in the pre-time situation on 205, and here it is on the right on 205 after the Swarm algorithm. So you could see that there was a pretty significant and imperative increase in the communication failures. So the way the Swarm algorithm works is that there's, at the central traffic management center, every 20 seconds from all of these ramp meters, so all 500 ramp meters in the area, or not, no, those are all 500 detectors. So from each ramp metering station, it's polling, give me speed, count, and occupancy from each of those stations. And previously, in the pre-time situation, that was all the system had to do. But now with Swarm running, it's also trying to send commands to change the ramp metering timing. And so this additional demand on the controllers that are running the ramp meter, and they're fairly old. They're 170 computers. They're not that snappy. And so this additional workload, basically, the communication failures end up being drops. And so there's and after we sort of pointed this out, ODOT was able to look at the log, and they found lots of commands that had been waiting to be issued or collected from the ramp meter controllers that weren't being, because there was an additional demand on the communication network. So this is not necessarily about the Swarm algorithm that caused the communication failures. This is about the ODOT communication infrastructure. And after they saw this, they made some fixes on a couple of the corridors where they were able to, the way the controllers work is they're sort of tied together in, they kind of communicate in series, and they were able to sort of separate some of those out on different channels and improve the communication. And so, and they did that mostly on 217, where I didn't go over it, but the communication was a little bit better there. So this is something they're aware of and that they're working on, but it was not something that they sort of anticipated as implementing the Swarm algorithm. So our conclusions, and this was an empirical sort of observational evaluation of the Swarm algorithm as implemented with the parameters that ODOT implemented in the field. We felt that on 205 the results were generally positive, but on 217 there was still some, that the results weren't that good, and that we were recommending, well, they definitely need to look at how Swarm has implemented the parameters. It has a number of different parameters that can be tuned, and they need to look at those, including maybe even allowing the adaptive ramp metering not restricting it to end at 9 and come on at 1, maybe let it run the whole day. And I already mentioned that the change in performance, particularly on 217, was due to the higher metering rates and the different freeway volumes and lanes. And I think the communications failures, like I mentioned, that was one of the findings of our evaluation. They weren't anticipating it. Now they're out trying to make some fixes in the system. And it's also important because that could have other, we use the freeway data for other traveler information programs, other evaluations, and so missing large chunks of data could have other impacts. So they recognize that improving the communication so that there's less drops is a good maintenance strategy. And also, it'd be very easy to sort of evaluate this on an ongoing basis with the archive data, but we needed a few more pieces of information sort of on a consistent basis. So one, it'd be nice to have those on-ramp counts at the top of the queue. They don't actually collect that information in the system now. So in the next rewrite of the TMOC software, including that information would allow you to measure on-ramp queues. Even though it failed in our data collection approach, we did a pilot test and it worked, and it should work. In theory, it was the way the program collected the data. But it also should log, the system should log the meter activation times and actual meter rates. So right now it sort of gets kind of lost in once it's issued or once it's recorded, there's no log of that. So if you wanted to go back and evaluate, well, what did Swarm do? There's really no way to do that without sort of trying to infer it from those plots that we looked at it. So the system, it could very easily say, at this time I sent this metering rate to this controller, and it should log those. And then you could evaluate the system over time. If you made changes to some Swarm parameters, you could see what the improvement or change on the corridor was. So again, I already mentioned acknowledgements. Rob Bertini was the PI on the project, and Oren Eshel, Cheng Yu, I left you. Forgot to type your name up. But Oregon Transportation Research and Education Consortium for funding the project. This was a joint project with ODOT. The National Science Foundation and the Career Award funded the development of Portal. And our technical advisory committee, Jack Marchant, Galen McGill, and Dennis Mitchell, Fuang. What's that? Nguyen, and June Ross. We always just call her Fuang. Bill Close and Paul Zabel. Paul Zabel helped us with the programmable logic controllers from the city of Portland. And Nathaniel Price and Amy Mastraccio, at ODOT, not FHWA. So with that, I will take some questions. Yeah, so.
I actually have two questions. The first one is,
Do you want to do that?
their initial Swarm settings from California settings?
No. Yeah, they attempted to tune them themselves. So.
And then the second question is, was this evaluation technique similar to one that has been done in California?
I mean, I don't know if it was the exact technique that they used to evaluate it. Do you know, Rob?
Ours was better.
It looked pretty good, so I thought it was very easy to comprehend.
These days, simulation is used a lot to evaluate, so this was unique in that it was purely empirical. There was no made-up data at all.
You didn't mention any kind of surveying, but I was curious if in the past, if they've done customer satisfaction surveys, how highway users feel about the rent meters.
So there's I don't know if it's famous, but there's a ramp metering study that was done in Minneapolis where the legislature was so upset by ramp metering. The Twin Cities has a pretty extensive ramp metering system. They ordered MnDOT to turn off all the ramp meters and do a month study. So if that's an indication of sort of public's perception of the meters, that's probably one. What they found is sort of what we found, that turning the ramp meters off caused much more delay. They also were able to evaluate safety. And so at that direction of the legislature, they were going to, if the study proved that the ramp meters were not doing their job, they were going to leave them off, but they're back on, although they did change some of their timing. So, I mean, it's if it's implemented right, it's an effective strategy and proven strategy. So.
Does the system encounter any emergency vehicle preemption or transit priority?
So no, there's no emergency vehicle preemption. If they needed to get by on the ramp, they could use the shoulder. The two corridors we looked at don't have any HOV bypass lanes. I think there's a couple on US 26 inbound. There's a couple HOV where the meters here are normally 2 lanes when the meter's on. There they've got a 3rd lane for buses and HOVs. So that's also a common implementation in other cities, but we don't have HOV bypass except for on a couple ramps. Yeah.
Chris, thank you. This was very interesting. And I don't know how exactly the swarm works, but could you please tell me what are the main parameters that swarm work with? I mean, to adopt the signal timing.
So, well, I could go back to that graphic, but it's mainly density. So it's trying not to allow too many vehicles to accumulate on the freeway. So that's the measure it's looking. It's looking downstream and at the local, measuring the density to try and, so as that goal to try and keep vehicles off the freeway below the critical density so that the freeway maintains performance.
And my second question is, do you think there may be some problems with the swarm algorithm if it requires an improvement to work better?
Yeah, I mean, there's a long list of sort of different adaptive algorithms and different strategies. So it could probably be improved, but we evaluated what was implemented, a field-based evaluation. We didn't actually, we didn't delve into the algorithm at all. We just evaluated what its outcome was. Yeah, Charles?
Just wondering, would some of the would swarm perhaps work better if there were, say, more metering stations along the freeway, say perhaps measuring exits as well as?
Yeah. Yeah, that's one thing. In the California implementation, they do have off-ramp counts, and so Swarm could perform better, as any sort of adaptive system could. With more knowledge, you would expect better performance.
My question is maybe from the literature. I don't know if you saw this in this study, but how sensitive is density, like a small change in density, affect the performance of Swarm or any other control? Is there any study of that, like small changes may have large impacts on performance? Or?
Yeah, I guess I'm not aware of that. So there probably is. Sort of, I joined the project after the lit review, so yeah.
There's substantial auxiliary lanes out on 217. And so do you think, when you were measuring your mainline lanes and not really focusing on the auxiliary lanes, and then what sort of an impact do you think that might have had?
So, that's another, I didn't mention that, that's another reason why 217, because of all the lane adds and drops and auxiliary lanes, it's sort of a completely different corridor. But the detectors are, if it's a long enough lane, it's measuring mainline lanes, not the auxiliary lanes. So, I don't know if that answers your question. Yeah. Yeah. Yeah.
There's a web question about enforcement. What kind of enforcement is used or applied at the ramp meters? And is there any, this is similar to Alex's question, but is there any public information about the ramp meters?
I've not, I guess I've only seen one enforcement activity at the ramp meters in my sort of history in Portland. So in general, I would say there's almost no enforcement of the metering times. I sort of have a funny story because as we were working on this project, my wife was teaching at the school in elementary in Beaverton, and the swarm algorithm, when the ramp metering changed, even though the ramp meters were off and the sign that said, no ramp metering, everybody was used to the ramp meters, so they were queued up and operating the ramp meters without the ramp meters. So I guess we're good drivers in Portland. So, and in terms of public information, I guess I'm not quite sure what they're asking, but
How are the public informed about the ramp metering system, how it works, its value?
They can go to its.pdx.edu and read our research reports. So, but there are, the Federal Highway Administration and the ITS program does produce a lot of information about it. In terms of freeway management strategy, this is kind of one of the big tools in your toolbox. So,
I think the questioner was getting at the public awareness aspect of this kind of a project. There's probably no effort put into public awareness.
Yeah.
But in the case of Minnesota, they embarked on a huge campaign to explain ramp metering to people during their experiment.
Yeah, right.
Try this one.
Does the swarm system take into account any changes in traffic pattern? Like, I suppose it doesn't necessarily with a lot of drivers that are exiting in like the inside lanes free service versus just overall density.
Yeah, it's overall density, but you can set parameters for each ramp and for the corridor. So in terms of tuning the algorithm, you could make some adjustments based on knowledge of the field conditions.
Has there ever been any consideration of putting like detectors in those lanes to like measure traffic density?
I mean, I don't know the exact situation you're talking about, but they are talking about moving the detector, the typical detector location, to more capture the disturbance at the ramp merge area. So all right, last question.
Yeah, I'm wondering how is the ramp metering implement every ramp. I guess if the ramp is close spacing, the spacing is quite close to each other, is a ramp spacing. The ramp meter probably can work well. If the longer spacing, the ramp is very long spacing, it may not work very well. I think it's a kind of a factor to consider the ramp spacing. I mean, if you want to reserve the flow to get on the freeway.
Yeah, I mean, I think so all the ramps, all the on-ramps are metered in the Portland metropolitan area. And I guess I'm not quite sure what you mean by how the spacing might affect the ramp metering strategy. I think it has a local effect and a corridor-wide effect. So metering effects, can improve the local condition by spacing out the platoons, and then it can also over long, corridors keep the demand accounts down. So I'd be happy to take any questions afterwards up here. So, but just to sort of go ahead and end here. So thank you for attending, and next week, Michael Berman.
Traveler information.
Traveler information. So thank you.